Hello friends, we have already dealt with the topic textile finishes. Today, let us study in detail about UV protective finish. The ultraviolet radiation from the sun is absorbed or reflected back into space by ozone layer in the atmosphere. Hence, only a little amount reaches the Earth's surface. But in recent years, the whole world is suffering from all kinds of pollution, consequently damaging the Earth's protective ozone layer. This reduction of ozone layer in the upper atmosphere has led to increased danger of exposure of skin to UV radiations, resulting in increasing risk of skin cancer. So, the importance of UV protective finish has substantially increased. The objective of this module is to understand about ultraviolet radiation and its effects, to understand the need, application and use of ultraviolet protective finish, to get an insight into the assessment and standards for UV protection, to learn about the factors contributing to the UV protection of textiles. What is ultraviolet protective finish? Ultraviolet protective finish is a specialty finish for protecting the fabric from UV radiation so that it protects the human underlying tissues from UV radiations. These finishes include chemical compounds that absorb energy in the UV zone of the electromagnetic range. Sun protective finish or UV blockers are other names for this finish. What is UV radiation? All of us know that sunlight is a natural source of energy that reaches the surface of the Earth. This solar radiation consists of infrared, visible light and ultraviolet radiation. Ultraviolet radiations roughly contribute to 10% of the sun's energy. Most of the harmful radiations emitted by the sun are absorbed by the atmosphere and only about 5% of the harmful radiations reach the surface of the Earth. Electromagnetic radiations of wavelength in the range of 100 nanometer to 400 nanometer are referred to as UV radiations or UV rays. Solar UVR that reaches the Earth's surface contains radiations in the range 290 to 400 nanometer due to atmospheric absorption of the shorter wavelengths below 290 nanometer. Based on the range of wavelengths, the UV radiations are categorized into three regions: UVA, UVB and UVC. UVA ultraviolet radiations in the range of 320 nanometer to 400 nanometer have longer wavelengths which on exposure to skin penetrates and generally causes wrinkling and speeds up aging of the skin. UVA accounts for 90% of total UV radiations reaching the Earth's surface. The shorter UVB radiations in the range of 290 nanometer to 320 nanometer is much stronger and dangerous to the skin and eyes than UVA. UVB radiations on excessive exposure penetrate few millimeters of the skin and corresponds to greater damage of the human skin like sunburns, redness and skin cancer. UVB is mostly absorbed by the ozone layer and only a small amount reaches the Earth's surface, but its potential in causing sunburn is much more than UVA. The most injurious to the skin and eyes are the shortest UVC radiations in the range 100 nanometer to 290 nanometer. It's completely absorbed by the atmosphere and does not reach the Earth, so it is not considered a health concern. Now that we have seen what is UV radiation, let us see the effects of UV radiation. First, let's see its effect on humans. Ultraviolet rays represent a small portion of the solar spectrum but affect all living organisms and their metabolism. Energy level is inverse to wavelength, so the UV radiations with the shortest wavelength in the spectrum possesses high energy and are harmful to the human skin and eyes. These radiations can cause a range of effects from simple tanning to highly malignant skin cancers if unprotected. Penetration of UV rays into the top layer of the skin leads to damage in the lower layer and prolonged exposure may lead to severe and chronic reactions and damage such as premature aging of the skin, wrinkles, photodermatitis, phototoxic reactions to drugs, erythema, sunburn, increased risk of melanoma, that is skin cancer, and eye damage. It can also cause DNA damage. And with decrease in ozone layer, these are expected to increase. This has forced the development of UV protection finish. Next, look into the effects of UV radiation on textiles. UV radiations is not only harmful to the living creatures, it is also responsible for deterioration in useful properties and service life of materials like textiles, furniture, etc. UVR accelerates the physical and chemical deterioration process of the polymer of textile product due to absorption of energy and ultimately leads to strength loss of the textile product, yellowing of cellulosics, photo-oxidation of polyolefin, etc. UV radiations also attack the dyes present in the goods, resulting in spotting and loss of color. The degradation can be reduced by using UV stabilizers which scatter the energy acquired from these ultraviolet radiations in the harmless manner, thus protecting the material and getting themselves destroyed in the process. Next, let us deal with ultraviolet protection. The stratospheric ozone absorbs the ultraviolet radiations from the sun and protects the earth from harmful radiation. But ozone is getting depleted due to the presence of air pollutants such as fluorocarbons, sulfur dioxide, carbon monoxide and hydrocarbons present in the environment. With increase in depletion of ozone layer, there is steady increase in the amount of UV rays reaching the earth. It's predicted that 1% decrease in ozone concentration will increase the rate of skin cancer by 2 to 5%. As too much exposure of these radiations leads to harmful effect, it's highly important to guard the skin. The best way to care for oneself against the harmful effects of UV radiations are avoiding outdoors, especially during midday, using sunscreen creams or lotions, and wearing protective clothes. Role of sunblock creams is to absorb or reflect UV rays. Apart from sunscreen lotions, textile materials and accessories made of textile materials are chiefly used for UV protection. Protection offered by UV protective clothing is more durable than sunscreens. The basic purpose of a garment is to protect the wearer from weather, but it is also a supreme means of protecting oneself from harmful UV rays. The UV rays incident on the fabric is absorbed, reflected or transmitted. Higher the transmission of UV rays through the fabric, lower is the protection offered by the fabric. The extent of protection of skin by textile materials greatly depends on the fabric structure. Protective effect of clothing can be improved by wearing thick materials, darker colors or several layers one on top of the other. The UV blocking property of a fabric is enhanced when a dye, pigment, delustrant or ultraviolet absorber finish is present that absorbs ultraviolet radiation and blocks its transmission through a fabric to the skin. Various nano finishes using titanium dioxide and zinc oxide also increase the UV absorbency. In order to achieve a balance between a high UV protection factor, wearing comfort and durability, in recent years special fibers with built-in UV protection have been developed. They contain titanium dioxide which reflects and or absorbs harmful UV radiation so that it does not reach the skin. Fabrics treated with UV absorbers ensures that the cloths deflect the harmful ultraviolet rays of the sun, reducing a person's UVR exposure and protecting the skin from potential damage. The extent of skin protection required by different types of human skin depends on the UV radiation intensity, the distribution in reference to geographical location, time of the day and season. This protection is expressed as SPF or UPF. Higher the SPF or UPF value, better is the shield against UV radiation. Sun protection factor, that is SPF. Sunscreens are rated by SPF. It is an assessment of the amount of protection provided by the sunscreen against UVR. SPF is a factor by which the period of exposure to sun can be extended without reddening skin. For example, SPF 10 means one can stay 10 times longer before burning than if one was wearing no sunscreens. It ranges from 2 to 50 plus. Ultraviolet protection factor or UPF. UPF measures the effectiveness of textile fabrics in shielding the human skin from UV radiations. It is expressed as the relative amount of time required for the skin to show redness with and without the textile material under regular exposure to solar radiations. If a person experiences skin redness on exposure to sun after 10 minutes, then on wearing a textile material of UPF 20, he would experience the same amount of skin redness after 200 minutes. A UPF score of 30 indicates that only 1/30th of the UVR striking the fabric surface essentially passes through it. Higher the UPF of a textile, the better is its ability to guard the skin it covers. A UPF value of 15 to 24 means good protection, 25 to 39 very good protection, 40 to 50 excellent protection, and 50 plus is the ultimate in UV protection. UV absorbers. UV stabilizers based on their method of action are classified into 3 different categories: UV absorbers, quenchers, hindered amine light stabilizers or HALS. HALS provides very good resistance against UVR. UV absorbers strongly absorb UV in the wavelength of 290 to 360 nanometer and provide good protection from UVR. UV absorbers are either organic or inorganic colorless substances that absorb UV light effectively and convert the energy into relatively harmless thermal energy without itself undergoing any appreciable irreversible chemical change or inducing any chemical change in the textile molecule. Ultraviolet absorbers have UPF rating of UPF 50 plus to UPF 500 plus. Organic UV absorbers. Organic UV absorbers are mainly derivatives of orthohydroxyl benzophenols, orthohydroxyl phenyl triazines, orthohydroxyl phenyl hydrazines. The orthohydroxyl group in the molecule helps in absorption and to make the compound soluble in alkaline solution. Organic compounds like benzotriazole, hydrobenzophenone, and phenyl triazine can be applied by normal padding or coating. Orthohydroxyl phenyl and diphenyl triazine derivatives have excellent sublimation fastness and self-dispersing formulation. It can be applied by pad thermosol process and also in print paste. The other one is inorganic UV absorbers. The existence of inorganic pigments in the fibers helps in better dispersion of light from the substrate, thus providing better protection. Metal oxides like zinc oxide as UV blocker are more stable when compared to organic UV blocking agents. The most common nanoparticles used to impart UV protection are zinc oxide, titanium dioxide, silicon dioxide, aluminum oxide, etc. They provide a protection benefit by reflecting, scattering, or absorbing harmful UV. Inorganic fillers are formed from microfine particles of titanium dioxide or zinc oxide that reflect the incident UV light like tiny mirrors. Zinc oxide nanoparticles. Zinc oxide has high absorption band. Apart from its exceptional UV absorption properties, zinc oxide has numerous other advantages like increased surface area. It does not migrate, it is not degraded by absorbed light, and may improve the mechanical, optical and electrical properties of the polymer. titanium dioxide nanoparticles. Titanium dioxide and other ceramic materials have high absorption power in the UV region of 280 to 400 nanometer and results in dispersion of UV rays and thus make it less permeable to UV rays. It also shows good photocatalytic and antibacterial property. What you see in the above table is our commercial UV absorbers. For practical use, UV stabilizers must demonstrate most of the following properties, that is maximum absorbency in the UV region, that is 280 to 400 nanometer, and no absorbency in the visible region. It must be stable towards electromagnetic radiation and should not get damaged or used up in fairly short time. It must disperse the absorbed energy in such a way so as to cause no degradation or color change in the medium it protects. Thermally stable to processing conditions and chemically inert towards other additives present during production and subsequent use. It should not be toxic. If used in sunscreen lotion, it must not irritate the skin. So next let's see how these UV blockers or UV absorbers are applied to fabrics. UV absorbers are compatible with dyes and are applied by normal padding, exhaust, pad thermosol or pad dry cure methods. UV absorber 30 to 40 grams per liter is applied at 60 degrees centigrade with 20 gram per liter sodium chloride using a padding mangle at 80% expression. After padding, the fabric is dried at 130 degrees Celsius for 5 minutes and cured at a temperature of 170 to 180 degrees centigrade for 3 minutes. Whatever is done must be tested to check its effectiveness, and the two types of test methods used to analyze the UV resistance of the fabric are in vivo for SPF and in vitro for UPF. In vivo testing involves tests made on the back of volunteers with healthy skin. In vitro testing makes use of a spectrophotometer in the range of 280 to 400 nanometer to calculate UPF of the material. The transmission of ultraviolet radiation through a specimen is measured on a spectrophotometer or spectroradiometer at known wavelength intervals. The UPF is calculated as the ratio of erythemally weighed ultraviolet radiation irradiance at the detector with no specimen to the erythemally weighed UVR radiance at the detector with a specimen present. There are various methods of measuring the UPF. They are the Australian New Zealand standard, the European standard EN 13758-1, American Association of Textile Chemist and Colorist Test Method, that is AATCC 183, and the UV standard 801. These tests standards define different conditions for the material being tested. The first three standards only require testing to be carried out on new textiles that are dry and unstretched. The UV standard 801 is considerably more practical for clothing textiles. The UPF is measured on the stretched, wet textile and after mechanical wear and tear caused by wearing and washing. Next, let's look into the factors that contribute to the UV protection of textiles. UV protection of fabrics depends upon the following parameters. The first one is fiber characteristics. Natural fibers generally have lower ultraviolet absorption than synthetic fibers. Grey cotton is found to offer greater protection than bleached cotton, obviously because of the presence of natural absorbers like pectin, wax, etc. Wool and silk absorb ultraviolet rays because of the presence of natural tannins and lignins. Wool has greater UPF among all the natural fibers. Generally, silk fabrics are found to be thin, hence they have lower UV protection than wool. Among synthetic fibers, polyester has maximum UV absorption because of its aromatic structure. polyamide fibers are less resistant against UVR. UVR property of synthetic fibers can be improved by using additives like titanium dioxide and UV absorbers prior to fiber extrusion in manufacture. Specialized fibers have been developed like sun modal fabrics with UV absorbent properties. Higher transmission of UV radiations is observed in the case of bright fibers like viscose than dull fibers. Next, let's look into the yarn structure. Twist of the yarn relates to the packing density of the fiber in the yarn structure. It corresponds to the air space within the fabric structure, hence contribute to the transmission of UV rays through the fabric. The yarn twist becomes one of the major determinants of UPF, especially for knitted fabrics, as it affects the porosity of the fabric. Regarding fabric construction parameters, fabric porosity is the most important parameter deciding the UPF of the fabric. Fabrics with closely packed threads are found to have higher UPF. The UPF is actually calculated as 100 by fabric porosity. Based on the above expression, it may be understood that UPF is highly correlated with fabric porosity. Porosity should be below 1.5 to 2%. In knit structures, the loop structure facilitates porous structure, hence transmits more UV rays than woven fabric. The weave or construction of fabric is the main factor affecting UVR coming through the fabric. The more closely woven the fabric, the less UVR is transmitted. Twill weave is much denser than satin or sateen weave. Due to its high compactness, twill have better UPF. Lightweight, loosely woven fabrics have minimum UV protection. The cover factor of the fabric is the main parameter for UV protection. UPF also increases with fabric weight and thickness. Heavier clothing minimizes UVR transmission by virtue of having smaller spaces between yarns, thus blocking more radiation, and thicker fabrics have better UV protection. The next is the effect of stretch. Stretch offers poor protection than inelastic fabrics as it increases the pore size and is found to increase the UV transmittance. Loose fit garments offer increased airspace between the skin and fabric, which reduces the transmittance of UV rays to the skin. Next, let us see the effect of chemical treatments. Dyeing modifies the proportion of UV light transmitted through fabrics and increase UV protection performance. Depending on the chemical structure, the absorption band of many dyes used to color textiles extends into the UV spectral region, and hence dyes act as UV absorbers and increase the UPF of the fabric. Fabrics with darker colors transmit less UV light than light colors, and darker shades of the same hue have higher UV protection ability. Increased concentration of dye of same color on same fabric leads to darker shade of fabric, which also increases the UPF. It is because more dyes were presented to absorb the UV light, thus lower transmission was achieved. For example, navy blue transmits less UV light than a light blue color. The next process, bleaching, lowers the UPF of cotton fabric as it removes the natural absorbers. Fluorescent whitening agents. Fabrics treated with this optical brighteners, that is fluorescent whitening agents, reflect or absorb UV rays, hence cater to better protection. The enzymatic treatment. Cellulase, widely used in biopolishing, removes protruding fibers from the fabric surface. It's found that the enzymatic treatment increases the UPF of the fabric. Moisture also has an influence on UPF. Wet fabrics have lower UPF. Water in the intersides of the fabric reduces the scattering effect, and therefore increases its UV radiation permeability. Laundering. It causes changes in physical properties of fabric and hence affects UV blocking performance. Shrinkage of fabrics occur after laundering in cotton fabrics as the fiber swells, closing the space. Finally, the specially designed absorbers is the strongest way to protect from UV radiation. Okay, then what are the applications of UV protective finish? Since the most probable time for long-term solar exposure is in summer, the articles for UV protective finish are lightweight woven and knitted fabrics intended for producing shirts, blouses, t-shirts, swimwear, beachwear, sportswear and the like. Industrial fabrics designed for awnings, canopies, tents, hats, umbrella, shoes, baby carrier cover and blinds may also benefit from UV protective treatment. The area of most rapid consumption of sun protective textiles is geotextiles, packaging textiles, production textiles and agricultural textiles. Characteristics of UV finish. It is a specialty finish for protecting the fabric from UV radiation. It protects humans' underlying tissues from UV radiation. It protects against short wavelength radiations, that is from 100 to 400 nanometer, non-yellowing or fading of fabric. It should be applied during dyeing under a reductive process. It's applicable by exhaust as well as padding method. I would like to conclude by highlighting a few points. Due to depletion of ozone layer, intensity of UV radiation reaching the Earth's surface has increased, affecting human beings, and therefore UV protection is definitely necessary. Human skin is vulnerable to UV exposure and hence needs to be protected. Sunscreen is applied to face, hands. However, other parts of the body require to be protected by means of UV protective clothing. These are developed through various finishing techniques using UV absorbing chemicals. There is a growing consumer demand for increased sun protection, which has driven the sun care market into innovative areas including UV protective clothing. So dear students, protect yourself from the harmful UV radiation using sun protective clothing. Thank you and bye for now.